Hello friends, welcome to your channel Crash Course for the Engineers. In the previous sessions, in the previous videos related to fluid dynamics, we had this derivation of Euler's equation and the Bernoulli's theorem. So on the screen you can see the Bernoulli's theorem is written. Now this theorem is written with the consideration of losses. So HL are the losses. If losses are not there, so this term will be equal to 0. Now this Bernoulli's theorem equation is P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2. Now talking about the applications of Bernoulli's theorem, it is applied in all problems related to incompressible fluid flow where the energy changes are there. Now, here in this video, we'll talk about the applications where this Bernoulli's theorem is applied in the measurement devices like Venturimeter, orifice meter, and pitot tube. This Venturimeter is a device used for measuring the rate of flow of fluid through a pipe. Venturimeters and all other three devices are used for closed flow. So flow through a pipe is there and I want to or we want to measure the flow rate. So here in that case we will use the venturimeter. Many of the times we want to find out the velocity of flow. So for that case also we use venturimeter. Now this venturimeter has three parts. First is a converging section. The length of this converging section is short. Then there is a throat. Throat is of same cross section area and it is having certain length, small length. Then there is a diverging part. Now if we look at this diagram, we can say that if we talk about the energy changes, so first we'll talk about the pressure energy. Now, when the fluid is flowing from left to right, in the convergent part, the pressure energy, if we are talking about the pressure energy, the pressure of the fluid decreases. It reaches to the minimum before the throat. In the throat, it should remain constant as the cross-section area is same. And in the diverging part, the pressure slightly increases. So this is the trend of the pressure in case of the venturimeter. Now, if we talk about the velocity, in case of the venturimeter, the velocity of the fluid, if suppose this is the inlet velocity, the velocity increases and it reaches to the maximum. In the throat, the velocity remains constant and the velocity drops in the diverging part. So this increase in the velocity is on the expense of the decrease in the pressure in the converging part. Now we'll go through the derivation which is related to the flow rate through the venturimeter. Now if we look at this diagram, there is a pipe, and from here the convergent section will start up to this point. Then there is a throat of certain length, and then there is a divergent. Suppose this at the start of the convergent part, we are saying this is the point number one or section one, and at the center of the throat, we are saying it is section number two. So suppose D1 is the diameter at inlet or diameter at section 1. So D1 is diameter at section 1. Same way as we have seen in the previous slide, suppose P1 is the pressure at section 1 and V1 is the velocity at section 1. As the pipe is a circular in cross section, so A1 is the cross-sectional area at the uh, section 1 can be written as pi by 4 into d1 square. And in the same way, d2 is the diameter at section 2 or at the throat. P2 is the pressure at the throat, and V2 and A2 are the velocity and area at the section 2. Now, if we apply the Bernoulli's equation, so Bernoulli's equation is P1 by rho g plus V1 square upon 2g plus Z1 is equal to P2 by rho g plus V1 square upon 2g plus Z. As you can see in the diagram, so this pipe is horizontal. So we can say Z1 is equal to Z2. So this cancels out. So we can rewrite this equation as P1 by rho g plus V1 square upon 2g is equal to P2 by rho g plus V2 square upon 2g. Now rewriting this equation, P1 minus P2 upon rho g can be written as V2 square minus V1 square upon 2g divided by 2g. Now here this term P1 minus P2 upon rho g is the difference of pressure head at section 1 and 2. Now if we are saying that a differential manometer is attached over here, then this term can be written as H. So that term can be found out by the analysis of the differential manometer. If we put this value in the above relation, so H is equal to V2 square minus V1 square divided by 2G. Now if we have got this relation, I want to find out, or we want to find out the discharge. So discharge is nothing but flow rate. Discharge can be written as A1 into V1 is equal to A2 into V2. So if we apply the continuity equation, applying the continuity equation, we know A1 V1 is equal to A2 V2. Or I can get V1 is equal to A2 V2 upon A1. So if we substitute the value of V1 in the previous relation, that is this relation, so we can get, so here H was equal to V2 square minus V1 square upon 2G. So we have copied this relation, right? So putting this value of V1 in the terms of V2. So what we are getting, V2 square minus A2 square V2 square upon A1 square bracket divided by 2G. So, so A1 square V2 square minus A2 square V2 square divided by A1 square whole divided by 2G. So this is the value for H. Now rewriting this relation for getting the value of V2 in terms of H. Okay, so if we rewrite this relation for V2 in terms of H, so V2 square is equal to 2GH A1 upon A1 square minus A2. So this is the relation for V2 square, or V2 is equal to under root of 2GH. Then, so here this square, so A1 upon under root of A1 square minus A2 square. Okay, so we got the relation for velocity at the throat, but we know Q is equal to A2 into V2. So if we put the value of V2 above value of V2, so the relation will change to A1 A2 upon divided by, that is A1 square minus A2 square into under root of 2GH. Now this is the relation for discharge under ideal conditions, and it is also called as a theoretical discharge. So suffix T is used. Now we know that the actual discharge will always be less than the theoretical discharge. So to find out the actual discharge, so Q actual, we add a coefficient of Venturimeter. that is CT. So the relation will be A1 A2 upon A1 square minus A2 square under root of into under root of 2GH. Now this is the relation for flow rate through the Venturimeter. It's a very simple derivation. As I told you, the value of H was given by the differential YouTube manometer. Now there are different cases depending on the liquid which is used in the Venturimeter. So if the the liquid which is used in the differential manometer. Now here there are two liquids. First liquid is flowing through the pipe, which we can say as a working fluid, and second liquid or fluid which is used in the manometer, differential manometer. So condition is if the manometric liquid is heavier than the liquid flowing through the pipe. So suppose mercury is used in the manometer and in the pipe water is flowing. So the SH is the specific gravity of heavier liquid. SO is the specific gravity of liquid which is flowing through the pipe. And X is the difference of the heavier liquid column in the U-tube. So the H can be found out. H is equal to X into SH divided by SO minus 1. Now the case 2 is if the differential manometer contains a liquid which is lighter than the liquid flowing through the pipe. So the first condition was SH is more than SO, and second condition is SAL is less than SO. So here H is for heavy and L is for lighter. So H, that is manometric head, can be written as, or here the value of Venturi head can be found out. H is equal to X into 1 minus SL upon SO. Now there may be a case where the manometer is inclined. So in case of an inclined uh, Venturimeter, a differential YouTube manometer is used. So the relation will change. So here H is equal to, now this value of H is nothing but P1 by rho G plus Z1. Now in case of the horizontal Venturimeter, the Z1 was equal to Z2. That's why the term of Z was not there. Now in case of inclined Venturimeter, the Z term will be there. So H is equal to P1 by rho G plus Z1 minus P2 by rho G plus Z2 is equal to, so other things will remain the same, X into SH upon SO minus 1 if the manometric fluid is heavier, and in the same fashion is equal to X into 1 minus SL upon SO. So this diagram tells us everything. Now uh, we have seen in the uh, previous slides the derivation for the flow rate or discharge through the Venturimeter. Now understand that on the basis of these things, there are simple uh, numericals where we want to find out the discharge through the Venturimeter. Understand that the orientation of the Venturimeter, that is horizontal or vertical or inclined, plays a very important role in the analysis to find out the flow rate. Now, friends, I hope that you are understanding things what I am covering. If you have any query, please post it in the chat box. I'll be happy to give the answers. Now, we'll solve the numerical horizontal venturimeter with inlet and throat diameters 30 centimeter and 15 centimeter respectively is used to measure the flow of water. The reading of differential manometer connected to the inlet and the throat is 20 centimeter of mercury. Now we need to find out the flow rate. Take CD is equal to 0.98. Now this, if we look at the numerical, it is the orientation is a horizontal venturimeter, right? And the CD value is given, so I need to find out the actual discharge through the venturimeter. Now, if we draw the diagram will be like this. So this is the venturimeter. So inlet diameter is given as this one section diameter is given as 30 centimeter and the throat diameter is given as 15 centimeter. Now here the differential manometer is connected and the value of x is given. In many of the reference books, the value is given as y. So x or y is 20 centimeter of Hg or mercury. So we'll write the thing, we have written the things which are given in the numerical. If we find out the area A1 and area A2, so area A1 will be equal to 5 by 4 into D1 square. Friends, either we can convert the dimensions into meter or we can continue to use the same dimensions of centimeter also. So there is no problem. So pi by 4 into d1 square, that is pi by 4 into 30 square. So please find out the value. The value I think is 706.85 centimeter square. Same way A2 will be equal to pi by 4 into d2 square. So that is pi by 4 into 15 square. The value is 176.7 centimeters square. Please cross check the values, whatever the values I have calculated. Now CD is given as 0.98. Now first what we'll go, we'll find out the difference of pressure head by using the manometric relation. Now understand that in the differential manometer, the liquid flowing is mercury and the water is flowing through the pipe. So SH is more than SO. Now the formula for H can be written as H is equal to X into SH upon SO minus 1. So we'll calculate the value. So H can be found out by using the value of H is given as 20. Now here the specific gravity or relative density of mercury is not given. Mostly widely used liquid in the manometers is mercury. So one should have the knowledge of mercury specific relative density. So 13.6 is the specific gravity of mercury and specific gravity of water is 1. Okay, so value of H can be found out as is equal to 20 into 12.6. So that value is 252 centimeter of water. Okay, now we have other things as per the formula for Q actual. So we can find out the value of Q actual. I hope you remember the relation. So Q actual is equal to C D A1 A2 divided by root of A1 square minus A2 square into 2GH bracket square. So what we'll do, we'll put all the values. So value is 0.98. The value of A1 was 706.85. The value of A2 is 176.7 whole divided by under root of the square of the area. So 706.85 square minus 176.7 square. Now understand that there may be uh, mistakes during the calculations. So uh, keep calm and do the calculation. Then 2 into value of G is 9.81 and the value of H that we have already found out. So 252. Okay, so we'll go to the next step. The value of the numerator that I have found out is uh, 866067593.36. Please let me know if the value is something different. If you are getting something different value, then it might be possible that you have committed some mistake. 499,636.9 minus 31222.9. Now, friends, if you have ES calculator, you can easily calculate the value in one go. So, at the end, the value is uh, equal to, now the value of this denominator I am writing. So, this denominator is 684.4. The numerator value remains the same. Okay, so last answer is 1257, then 56. Okay, so centimeter cube per second. So this is the value of discharge, actual discharge. We have the habit of writing the discharge in terms of liter per second. So converting this into liter per second. So what I need to do, I need to divide this answer by 1000. So I'll divide it by 1000. So what I'm getting here is now this answer will be equal to 125.756 liter per second. Now, see friends, we have solved this numerical. The Venturimeter was horizontal, so it was easy to find out the values. Now we'll see one problem of each category. Now this is the different numerical. Here if you look at the numerical, find the discharge of water flowing through a pipe of 30 centimeter diameter, placed in an inclined position where the venturimeter is inserted, having a throat diameter of 15 centimeter. The difference of pressure between the main and the throat is measured by liquid of specific gravity 0.6 in an inverted YouTube, which gives the reading of 30 centimeter. Now, to give more difficulty, in the numerical, the loss of head between the main and the throat is given as 0.2 times the kinetic head of the pipe, and we want to find out the discharge. Now, the discharge can be found out here. The CD value is not known, so we are finding out the theoretical discharge. Now, as I asked in the previous slide, the orientation of the Venturimeter, you can see in the numerical it is given inclined position. So it is a inclined Venturimeter. Second is CD is not given. So we need to find out the Q theoretical value. Okay, so firstly we'll draw the diagram. The diagram may be simple. Okay, so this is the Venturimeter which is inclined as per our convention. This is one and this is two. Now there he is saying that the manometer is connected in between, and it is an inverted YouTube manometer. So uh, you know that this may be the construction of a YouTube manometer which is inverted. Okay, and the value of x is given. X is equal to 30 centimeter, and in this inverted manometer, the liquid is flowing with the specific gravity 0.6. So the third condition I told you to check whether the specific gravity of the liquid which is flowing through the manometer is less than the pipe liquid specific gravity. So we got our three conditions. Now here, as it is a theoretical case, so we need to apply the Bernoulli's theorem. We'll go step by step. So now D1 is equal to 30 centimeter. So we can find out the value of A1 as 706.85 centimeter square. Then D2 is given as 15 centimeter. So I can find out A2 is equal to 176.7 centimeter square. Okay, so I hope that you have calculated the values. Now x is given as 30 centimeter for inclined venturimeter. Uh, as we know, the pressure head, difference of pressure head can be written as H is equal to P1 by rho G plus Z1 minus P2 by rho G plus Z2. Now we have one more relation for H. So H can be written as it is equal to X into 1 minus SL upon SO. So this can be found out as X value is 30, 1 minus SL is 0.6, and the water is flowing through the differential manometer. Sorry, water is flowing through the pipe. So we can get the value as 30 into 0.4. So that can be written as 12 centimeter of water. So we got the value of H as 12 centimeter of water. Now in the numerical, if you look carefully, the loss of head between the main and the throat is 0.2 times the kinetic head of the pipe. So as I started this video with the Bernoulli's theorem with the losses, so here I can write out that HL head loss is equal to 0.2 into the kinetic head of pipe. So that can be written as 0.2 into the velocity in the pipe is V1, so V1 square upon 2G. Now read carefully, the kinetic head of the pipe is written, so I am writing V1 square by 2G into 0.2. So applying the Bernoulli's theorem, we know P1 by rho G plus Z1 plus V1 square by 2G is equal to P2 by rho G plus Z2 plus V2 square by 2G plus HL. Rewriting this equation, so what we want, okay, so P1 by rho G plus Z1 minus P2 by rho G plus Z2, because we know this value is nothing but our H, so we can put this value plus V1 square upon 2G minus V2 square upon 2G is equal to HF. Okay, so we can get from here is 12.0, the value of H for P1 by rho G plus Z1 minus P2 by rho G plus Z2 plus V1 square by 2G minus V2 square by 2G is equal to, what is the value of HL? So 0.2 into V1 square by 2G. So what we are getting here, this is the relation number, suppose 1. Okay, now we want that we are not knowing both the velocities. So first we'll use the continuity equation to express one velocity in the form of another. So uh, by continuity equation, I can write A1 V1 is equal to A2 V2. So V1 is equal to A2 upon A1 into V1, sorry, V2 here. So we know the areas. So I can put the value of areas here. So I can get it is equal to V2 by 4. Now if I put the value of V1 as V2 by 4 in the relation number 1, so what we are getting 12.0 plus the value of V2 is V1 by 4. So we can write it as V2 square by 8G minus V2 square by 2G is equal to 0.2 into V2 square by 8G. Okay, so this relation can be written as, so we can take this term on the left hand side. So 12 plus V2 square by 2G into 0.8 upon 16 minus 1 is equal to 0, or the value of V2 can be found out to be 157.4 centimeter per second. I hope you are following the things. Uh, these are the things that you can put in the calculator to get the value of V2. V2 can be termed as X. So discharge or the flow rate can be found out as Q is equal to A2 into V2. So A2 is 176.7 into 157.4. So that value is 27,800 centimeter cube per second. So I can write it as in the form of liter per second as 27.8 liter per second. Now, friends, I hope you are understanding these numericals. First case was related to the horizontal case of the Venturimeter, and second case was related to the incline case, where the value of theoretical was found out by using the combination of Bernoulli's theorem and the continuity equation. Now, the next numerical, uh, it is written like this: a vertical pipe conveying oil of relative density 0.8. Two pressure gauges has been installed at A and B, where diameters are 160 millimeter and 80 millimeter respectively. Now here something is new is given. Point A is 2 meter above point B. The pressure gauge readings have been shown that the pressure at B is greater than at A by 0.981 Newton per centimeter square. Neglecting losses through the pipe, find out the flow rate through the pipe. Now, as I told you, first is the orientation. It is a vertical Venturimeter. Second is the value of CD is not given, so I need to find out the theoretical value of discharge. And now we'll go, we'll draw the diagram. So, so suppose this is a point A and this is point B. Okay, so point A and B, the distance is 2 meters. The diameters are given. So the diameter at A is 160 millimeter and diameter of B is 80 millimeter. Now, one more thing is given in the numerical. The relative density of oil is 0.8. So oil is flowing through the uh, this pipe. Also, the pressure at B is greater than at A by 0.981 centimeter square. So PB is greater than PA by 0.981. So I can write PB minus PA is equal to 0.981 Newton per centimeter square. So first, also, if we look at the numerical, what things are given. So first we'll find out the area. So The notation will be dA is given as 160 mm. Now we'll convert it into meters. So 160 means 0.16 meter. So A can be found out to be pi by 4 into 0.16 square is equal to 0.0201 meter square. In the same fashion, AP can be found out as pi by 4 into the diameter of B at B is 80 millimeter, that is 0.08 meters. So the area can be 0.00502 meters square. Now, if we look at the numerical, I have already told PB minus PA is given as 0.981 Newton per centimeter square. I want it in Newton per meter square, so I will multiply it by 10 raised to the power 4. So the value will be equal to 9810, right? So the conversion factor is Newton per centimeter square is equal to 10 raised to the power 4 into Newton per meter square, right? So applying this Bernoulli's theorem, Bernoulli's equation, PA upon rho G plus V1 square by 2G plus Z1 is equal to PB upon rho G plus V2 square upon 2G plus Z2. So I can rewrite it as PA minus PB upon rho G plus ZA minus ZB is equal to VB square minus VA square upon 2G. So putting the value of PB minus PA, the PB minus PA is 9810 divided by 800 into 9.81. Okay, now the value of PB minus PA is given, so I need to add a negative sign over here. ZA minus ZB, so point A is at a 2 meter above than point B, so it is equal to 2 minus 0. Reference will be point B, so I can write it as equal to VB square minus VA square upon 2G. So finding this value, it is minus 1.25 plus 2, that is 0.75 is equal to VB square minus VA square upon 2G. Now here, what we do, continuity equation. In many of the cases, the continuity equation helps us. So continuity equation is AA into VA is equal to AB into VB. So I can say that VB is equal to 4 times VA. Putting this value of VB as 4 times VA, what we get? So 0.75 into 2 into 9.81 is equal to, so the value will be equal to 16 VA square minus VA square, that is 15 VA square. So the value of VA is equal to 0.99 meter per second. Friends, calculate this value. Please check whether the correct calculations are correct. Q is equal to VA into AA. So the value is 0.99 and AA is 0.0201. So the discharge is 0.01989 meter cube per second. So this is the value of discharge. Now, friends, I hope you are understanding this theory part and the numerical part. We need to understand the theory and we need to understand the numericals also. The values which I have calculated uh, are already calculated by me. So if you find that the values are something different, you are getting different values, put in the chat box. If you have any queries regarding the theory or the derivations that I am covering in the derivation or the theory part, you can tell me. Now, this Venturimeters are used in many industries where the water is flowing in chemical, pharmaceutical industries, oil and gas industries. Now, in many of the cases, in many of the places, we find venturimeters are used, but they are limited because of the construction, the high cost of the venturimeter. That's why the next flow measurement device comes into picture, which is called as orifice meter. In the next session, we'll talk about the orifice meter, construction of the orifice meter, and we'll solve numericals on the orifice meter. Friends, if you are liking the content that I'm posting, please subscribe the channel. Okay, that will give me motivation to post new videos related to other subjects of mechanical engineering. Thank you.